Hey everyone, welcome to The Explainer. I'm so thrilled you're joining us today because, well, we're going to be looking at something that is literally hiding in plain sight all around us. When we think of basic geometry, we usually just picture simple static shapes, right? A square, a circle, a triangle. But what if I told you that one specific shape isn't just a shape at all? It's actually a master architectural blueprint. Today, we are deconstructing the parallelogram. We're going to look at it not just as lines on a page, but as this dynamic set of rules that practically governs the foundation of geometry itself. All right, let's dive right in. Okay, so here's our roadmap for today. First, we'll cover the prime directive. Then, the 5 structural pillars. After that, inheriting the DNA. Then, we'll test your knowledge with the blueprint pop quiz. And finally, wrap up with the quiz answers revealed. Let's get to it. Section 1. The prime directive. Okay, so every great architectural structure starts with a core rule, right? And for our shape, we call this the prime directive. Check out how simple this directive actually is. A parallelogram is born from literally one strict rule. Opposite sides absolutely must be parallel. That's it, the whole shebang. If you look at the red arrows on those top and bottom lines, they're showing us that the trajectories of these lines remain perfectly equidistant all the way out to infinity. Basically, they're never going to cross paths, no matter how far you draw them. And the exact same goes for that secondary pair on the sides. Everything else, literally every fascinating property we're about to cover, is just a structural inevitability of this one single rule. But before we build the house, we gotta know what lot we're building on. So technically speaking, a parallelogram is strictly defined as a convex quadrilateral. Now, quadrilateral just means it has 4 sides. Simple enough. And convex, that just means it doesn't cave in on itself. Every single interior corner pushes outward, which keeps all the internal angles strictly under 180 degrees. So this is our base category. It's the canvas we're working on today. Moving right along to section 2, 5 structural pillars. All right, so the prime directive is set. We've got our parallel boundary lines, and because of that, the whole structure just locks into place, creating this super reliable framework. These 5 pillars, they're basically the unbreakable laws of the parallelogram. Number 1, parallel opposite sides. That's the boundary we just talked about. Number 2, congruent opposite sides, which dictate our dimensions. Number 3, congruent opposite angles, controlling the internal corners. Number 4, supplementary consecutive angles, also known as the 180-degree rule. And number 5, bisecting diagonals, acting as the internal scaffolding. Okay, let's actually break these down visually, because seeing them in action really makes all the difference. Okay, look at this. This brilliantly illustrates pillar 2, mirror dimensions. Because our top and bottom lines are parallel, and our left and right lines are parallel, the distance between them is completely locked. What that means is the opposite sides are strictly congruent. They are literally perfect mirror images across the spatial divide. So if the top side is exactly length x, well, the bottom side has absolutely no choice but to also be length x. If the left side is length y, you guessed it, the right side is length y. It's just an inescapable architectural law. Moving right along, we hit pillar 3, opposite equality. Now, just like the sides mirror each other, the angles do the exact same thing, but diagonally across the internal space. So look at that top left corner, the one in red. If you shoot a diagonal line straight through the empty space down to the opposite corner, which is also in red, you'll see those 2 angles are perfectly congruent. They are exact structural replicas of one another, and of course, the exact same thing is true for the 2 green angles. Now we get to how these angles interact with their next-door neighbors, which brings us to pillar 4, the 180-degree rule. Any 2 consecutive angles, meaning 2 angles sitting right side by side along the exact same edge, are supplementary. They will always lock together to form exactly 180 degrees. If you take a look at the protractor graphic here, you can see that if the red angle is 135 degrees, the green angle directly next to it just has to be 45 degrees, because 135 plus 45 equals a perfect flat 180. This is kind of the mathematical glue that proves those sides are truly parallel. Finally, let's peek inside the shape at pillar 5, the internal scaffolding. If you draw 2 diagonal lines connecting those opposite corners, they are going to cross at an exact center point in the middle. Now, what's really amazing here is that these diagonals bisect each other. Literally, they slice each other perfectly into equal halves. Notice how one of those full lines is way longer than the other? That's completely fine. The full diagonals do not have to be the same length, but the exact point where they cross will always, without fail, cut both of them perfectly in 2. Section 3, inheriting the DNA. So, now that we've fully grasped this master blueprint, we get to see how it actually evolves. Like, what happens when you take these 5 unbreakable pillars and add a few extra, highly specific upgrades? Well, you get an entire family tree of shapes that inherit this exact same DNA. Rectangles, rhombuses, squares, they aren't just completely different random entities. They're actually all special classifications of parallelograms. Think of them as the offspring of our master blueprint. They inherit all 5 of those foundational pillars we just studied, but then they introduce their own highly symmetrical upgrades to the architecture. Let's put them side by side and see how this builds. All right, check out our diagnostic matrix here. Notice how in those top 4 rows, every single shape checks the box for the baseline parallelogram pillars. But, and here's the fun part, look at the upgrades at the bottom. A rectangle steps things up by forcing all 4 angles to be exactly 90 degrees. A rhombus, it goes a totally different route. It doesn't care at all about 90-degree angles, but it forces all 4 sides to be perfectly equal in length, and it makes those internal diagonals cross at exactly 90 degrees. And then there's the square. The square is basically the ultimate perfectionist of the family. It inherits absolutely everything. 4 right angles, 4 congruent sides, perpendicular diagonals. It is the maximum upgrade. Moving to section 4, the blueprint pop quiz. Okay, you've seen the blueprint, you've studied the pillars, and you've got the DNA down. Now it's time to put all that architectural knowledge to the test. Let's jump right into the blueprint pop quiz. I'm going to throw 5 rapid-fire questions at you based on today's explainer. Just lock your answers in mentally, and we'll review them all right after. Ready? Okay, question 1. Think back to those internal corners. If one angle of a baseline parallelogram is 45 degrees, what is the exact measure of the consecutive angle directly next to it along the same edge? Hint, keep pillar 4 in mind for this one. Moving to question 2. Earlier, we talked about how top and bottom and left and right relate to each other. So, which specific structural pillar ensures that opposite sides act as perfect replicas of one another across that spatial divide? Try to think about the dimensions here. Here's question 3. Just a quick true or false for you. Picture the internal scaffolding inside a standard baseline parallelogram. Actually, scratch that. I mean just a regular parallelogram, not a rectangle. True or false, its internal diagonals must always be the exact same total length. What do you think? All right, question 4. Let's look back at that family tree. Which special variant inherits the baseline DNA and adds exactly 4 right angles, but does not strictly require all 4 sides to be the exact same length? Try to visualize that diagnostic matrix we just looked at. And finally, question 5. This is definitely the tricky one. According to our diagnostic matrix, which 2 special shape variants feature internal diagonals that cross each other perfectly at a 90-degree perpendicular angle? Go ahead and lock in those 2 shapes. Section 5. Quiz answers revealed. Okay, the inspection phase is officially over. Let's see how well you grasped the blueprint. Time to reveal those answers. Here we go. For number 1, the consecutive angle would be 135 degrees because remember, they absolutely must add up to 180. Number 2, that was pillar 2, congruent opposite sides. Number 3, that is a resounding false. The diagonals definitely bisect each other into equal halves, but one full diagonal is usually way longer than the other. Number 4, a shape with 4 right angles but varying side lengths? That's your classic rectangle. And number 5, the 2 variants with perpendicular diagonals are the rhombus and the square. Honestly, if you got those right, phenomenal job following the structural logic today. Let's bring this whole thing together and look at the master blueprint just one last time. This single image is basically the complete anatomical profile of a parallelogram. We started with parallel boundaries, right? And that one rule forced our sides to be equal, it forced our opposite angles to mirror one another, our consecutive corners to sum to 180, and our internal diagonals to meet perfectly in the middle. It's just incredibly satisfying to see how one simple rule creates such a robust, literally flawless system of geometry. So as we wrap up, I really want to leave you with this thought. Now that you actually know the invisible rules holding this shape together, take a second to look up from your screen. From the angles of a massive suspension bridge, to the tiles on your kitchen floor, to the very structure of the building you're sitting in right now, where else do you see this shape DNA in the architecture of the real world around you? Once you learn how to read the blueprint, you realize the math is literally everywhere. Thanks so much for learning with me today, and I will catch you on the next explainer.